Before I get started on this question, I'd like you to pause the video and read it again so you can understand exactly what's going on here. So we've got some children, some of whom have the sickle cell trait, some of whom don't. And if I notice the children that have the sickle cell trait, that's 136, 407 don't. If I add those two numbers up, that's the 543 children we're talking about. And I'm curious if the proportion of malaria infections is the same for those two groups, or in fact, if it's lower among children with the sickle cell trait. So I'd like to start off with a hypothesis test. HO, P1 equals P2, and HA, the proportion of children with sickle cell who get malaria is less than the proportion of children without sickle cell who get malaria. So P1 is the proportion of children with sickle cell who get malaria or who are found to have that malaria infection. And P2 is the proportion of children without sickle cell who get malaria. Now I'm going to head towards a two proportion hypothesis test, but I need to check my conditions out first. First of all, I hope the children were randomly selected. It doesn't really say how they were selected, so I hope the two groups of children are like independent SRSs. Hopefully that's the case. Next, I want to check the large counts rule. And for the large counts rule, I need 10 successes and failures in each group. I have that, and I'll show you in just a second. I have at least 10 successes and failures in each group. Now, that's not sufficient to say that. I've got to tell you how many I've got. So for the first group, the children with sickle cell, I've got 36 successes, 36 and 100 for sickle cell children. And then with the not sickle cell children, I've got 152, 152, and the difference there, 407 minus 152, 255 for non sickle cell. So there I've checked my large counts rule. That's the one that gives me approximate normality. And then finally, there are clearly more, certainly, there are more than 10 times these numbers. Certainly, there are more than 136 times 10, so 1360 African children with sickle cell and was it 407? So 4070 without. So since these conditions are met, I will use the two sample Z procedures for proportions. So from here, I'll go into the mathematics. And so my Z test statistic is going to be P hat 1 minus P hat 2 minus P1 minus P2. all over. Now, this is where it gets a little interesting because on the z-test statistic, I use the pooled p hat down here. So this is p hat 1 minus p hat over n1 plus p hat 1 minus p hat over n2, where p hat is the number of successes, which was, let's see, 36 and 152 over the total number I'm looking at. So that's 188 over 543. Now, you're welcome to use decimals on here if you want, or you could use fractions. I think I'll go ahead and use fractions for when I write it, but it really doesn't matter. So here it is with the numbers plugged into it. In fact, this might be helpful to you up here if I went ahead and wrote p hat 1 equals 36 out of 136, and p hat 2 equals 152 out of 407. It's actually acceptable just to write the formula as long as it's obvious what numbers are to be plugged in where. So saying something like this and this up here at the top that I just did, this stuff here, is critical if you're not going to write this next step. But I'm going to go ahead and write it. So this is 36 out of 136 minus 152 over 407 minus 0 over, it's going to be a big old giant square root here, 188 over 543 times 1 minus 188 over 543, all over the first group. And then the second group, 188 over 543, 1 minus 188 over 543, all over the second group. Now again, like before, I'm not actually going to do this out the long way. I'm going to grab my calculator and I'm going to press stat test to prop z test. I'll enter my information like that. Notice it doesn't ask me if I want a pool here like it did on the means problem, because we automatically want a pool when we start out with this original null hypothesis that they're equal. If our null hypothesis is that the two groups are equal, that is pooling as far as proportion problems are concerned. So I've typed the information in my calculator. I hit calculate. Notice the one-sided test. Calculate, I get this information. There's no degrees of freedom here because it's a z-test, not a t-test. And so my z-test statistic is negative 2.31. My p-value is 0.0105. And this bit right here, that's what should remind you. Not only do I have a p hat 1 and a p hat 2, but I've got a p hat. That's 188 over 543 is that number right there. And so now finally I need to write a conclusion in context. And so my conclusion will be this. That's a pretty small p-value. So since my p-value is so small, how small is it? P is 0.0105. Now, if you had an alpha level of 0.01, this wouldn't be small enough and your conclusion would be the opposite of mine. Since my p-value is so small, I will reject HO in favor of HA. And so what does that mean? That is, I find statistically significant evidence that children with sickle cell, perhaps I should say African children with sickle cell since that's where I obtained my sample, have a lower percentage of malaria infection than children without sickle cell. There's how you do a two sample Z procedure for proportions.